So today we'll be discussing linear regression and introducing vectorized notation leading up to optimization. So we'll motivate why we perform optimization from what hopefully is an intuitive perspective. This will be a continuation of the first video, which discussed the basics of the linear regression model. So if you have not watched that, I recommend that you do. Okay, so let's just jump right in where we left off with the previous video. And that would be here. We had our basic model where y was the price of a house, x1 was a feature which could be the number of floors in the house, and beta 1 was a parameter which we were fitting our model to. So we would predict the price of a house based on the number of floors times this parameter. And then x2 would be another feature. Beta 2 would be another parameter associated with that feature, so on and so forth. So, let's take this, and we're now going to work on vectorizing our notation. So let's do that. So we're going to rewrite this equation by just simply taking the beta 0 from the front and putting it in the beginning. Nothing complex about that. Now, let's go ahead and do a little more manipulation. And this time we're going to just take the beta 0 and multiply it by a 1. So now we have 1 times beta 0. So all these three equations are the exact same. Hopefully we can agree on that. And let's take it a step further. And let's define what our vector beta is. We're going to define a vector beta here to motivate our vector notation. Our vector beta is just going to be all the betas packaged in as a vector. And you use these brackets to denote that this is a vector. You also use this symbol, this arrow above the beta, to denote that this beta is a vector. And these betas are scalars. Beta 0, beta 1, beta 2, and beta 3 are just numbers as you're taught in grade school. And that's it. We have our vector right here. Now we're going to denote another vector, and that's going to be our vector x. And our vector x is going to be similar. It's going to have the same size, 4 elements, and it's again a vector as denoted by the arrow on top. The first element is going to be a 1, and you can see why we're doing this for mathematical reasons, because we want this and this to line up. We want this and this to line up. We want this and this to line up, and this to line up, so that we can recreate what we have here. And now we're actually going to just multiply our two vectors, beta and x, and we're going to multiply them element-wise and take the sum of the product. So beta 0 times 1 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3. And what I just went through was actually exactly what you have right here. And this, what I just did, is the definition of the dot product. So what we just did was we took the dot product of beta and x. So we took x dot beta, which would be the same as beta time dot x. And to be very particular, one of these would have to be transposed, but forgive me for not doing so. So x dotted with beta. This is the definition of the multiplication, the dot product between the two vectors. And this is the exact same as this, meaning that we wrote out we created the formalism for two vectors, beta and x, which when you take the dot product of the two, we recreate our value y. So hopefully that was enough motivation to show you that y can be written as x dotted with beta. Now I need to pause. And now picking up where we left off, we have this vector notation where the price of a house is going to be the vector x of features times the parameters beta that best suit our model. And this is our model now. And what's beautiful about the vector notation is that you can have many features and betas. You can have an infinite number, and you represent them in this compact notation. So now we've set up this beautiful compact notation for writing it, and we have to now discuss how we're going to use this with many data points. Because remember, our objective is to find the set of parameters in the vector beta. And when I say that, I mean beta 0, beta 1, beta 2, and beta 3 that best fit our model over many different data points, many different houses. Right now, the way it's written, this is our model for one particular house. You get the price of one house by multiplying the features of that one house by the parameters beta. So let's say we have a vector x of feature values for one house and a price y for that house. As we said, we just need this set of parameters beta. But before we do any math, let's remember that we need to optimize our model over all the houses that we have, the full data set of houses. So we can't just plug in our values for y and x and solve for beta to make the model work for all houses. If we could, then that would mean we had a perfect model. And we know that's not true. And let's just think up of an example of why that can't be true. You could have two different houses with the same feature values, x, and of course the parameters beta would stay fixed, but they could have the same number of floors, the same square footage, they could both be in the same area, but have different prices. And therefore, just using this thought experiment, you realize that a model is very unlikely to be perfect. There's no way that our model would be able to work on both the houses in this example because they have the same exact features but different prices. Our model wouldn't know why the prices were different. And that would probably be due to us not having included enough features. But the point remains that we can't always ensure that the model holds. So therefore, we have to add a little bit of leeway for error to our model. And we simply add an error term. And we usually use epsilon to denote error. And so let's do that. We're just adding an epsilon to denote error in our model. So the price of a house is going to be the features times the betas plus some error term, because we're not going to get it right. We're almost never going to get it right. And this error term is how far off we are from the true value. Now, and this error term is a scalar. It's just one number. The price is also a scalar. These are vectors, but when you multiply these two vectors using the dot product, it returns a scalar, as you see here, because we take the multiplication of the individual numbers and then we add them up. So now let's get back to optimizing our model. Another way of stating that we want to optimize our model is by stating that we want to reduce the amount of error in the model, right? Because if we reduce the error, then the original equation here would always hold, and our model would be perfect. We'll never get perfect, but we want to get as close to perfect as we can by minimizing the amount of error here. And so we're going to do that through mathematical formalism. Let's first start by solving for epsilon, and this is just basic algebra that you would know from high school. And so here we go. We just take this term and subtract it from both sides. So epsilon is y minus x times beta. And now in order to optimize our model, we want to find the values for the vector beta that will minimize our error epsilon. And let's remember that at the end of the day, after we optimize over all values for the many different houses, right? So this is one formula that's for one house, right? But we're going to have to do it for many different houses. So we're going to have to work on developing the notation a little bit for that. And for each house, of course, there's a different x, y, and epsilon. So to restate, we're going to have to optimize this equation over many different houses. Every house has a unique x. Hopefully it has a unique x, a unique y, and a unique error. So it has different features than other houses, and it has a different price, and it has a different amount of error for the model. But we're optimizing our model to reflect all houses. So there's going to be one set of parameters beta for all of the houses. And that's what really defines our model, this beta. And then we can then take that beta and plug it into our model, given a set of features for a particular house to predict the price. But there's one beta that works for all houses, or that is optimized over all houses. So now we have to do this for all houses, right? And as we said, each house has its own epsilon, its own y, its own x. So we're going to denote each different house's epsilon, y, and x with a sub I. And what this means is that for house I, the error is going to be the price of that house minus the feature value for that house times our vector beta. That's it. So this is just taking this and making it unique to one particular house. And then we can go through all houses by switching up I. I can go from 0 to 100 if we have 100 houses. So it'll be 0, 1, 2, all the way up to 100. Beta will always stay the same. All right. Now, we have to be a little careful here, because now we have this error, right? And we have to think about it. We can get positive errors and we can get negative errors. And what is the significance of a negative error? We stated that we want to minimize the error. So it sounds like if we get a negative error and we want to minimize error, that's a super great thing. But really it's not. We don't want a negative error. We want to get the error as close to 0 as possible, right? We don't want it less than 0. But the mathematics behind optimization isn't going to understand that. So we want to take the magnitude of the error, or, we want a way to just measure how far the error is from 0. Is a good way to put it. So one way to do this is by squaring the error. So let's do that. Let's just square the error. And let's do that right here. We just square both sides. So if we square the error, the term here is always going to be positive because anything squared is, unless it's 0, is going to be positive. And if we're optimizing the square of the error is the same as optimizing or is very similar to optimizing the error itself. If we minimize the square, we're also minimizing the error. If we're minimizing the square of the error, we're also minimizing the error itself because they're proportional. And so this is the cost function here. And now we've seen how we've developed it. So let's go forth and minimize our cost function. All right. Now, keep in mind that we want to do this for all houses, right? So we have to, what we're going to do now is we're going to add up over all houses. And so this symbol sigma sub I just means that we add up over all the values of I, which are all the houses. So we're going to add up the squared error, that's all it's saying, for all houses. That's it. That's all this means. And we want to minimize the squared error over all houses. And that, written in mathematical notation, is just this. By the way, this is just the equation you saw from before. Nothing new here. So let's just bring them together. It's just the right-hand side. We're minimizing, but let's be very, this is the mathematical notation. We're minimizing this cost function by varying the parameter beta. So this is what we're minimizing, but we're minimizing it. We're minimizing the squared error. We're minimizing the error of our model by tweaking the parameter beta until we find the beta that makes this achieve the smallest value. Now, you can solve this mathematically using some calculus, or you can solve this through gradient descent or some other computational optimization methods, whatever you choose to use. But at the end of the day, this is it. This is the formula. This is the optimization that you're performing. And this is how you perform linear regression. And when you optimize this, you'll get a set of parameters beta. And what do you do with those parameters beta? You take those betas and use them in your original equation right here. Because for a house, you'll know what the features are for your house. And now you've optimized, you've obtained the betas, and it'll spit out a price X for you. And remember, this equation is the same as this equation up here that we started with. And that is it. All right. Thank you for listening.